Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear. This is my continuing feature on the Math Lovers book. And yesterday I started chapter 5, which is on sets. And in my last video, I introduced sets, I defined them. Today I'm going to talk about some basic operations on sets. I guess you should think of sets a little bit like numbers. Numbers are very basic to math. They're usually the first thing you learn about in math. And then once you learn what numbers are, you learn, certain types of operations like addition, subtraction, multiplication, and division. And you also learn things like order, less than or greater than or equals. Well, it turns out sets also have operations, which are kind of similar to those operations. Anyway, let's just begin. So the most basic types of operations on sets are what are called union and intersection. And if you have two sets, and here I give an example, A equals the set 1, 3, 5, 6, and B equals 2, 3, 7, 8. And what the union means, the union is just a set of all elements that are common to both sets. So that would be, in this case, 1, 2, 3, 5, 6, 7, and 8. You can see that each of those numbers belongs to at least one of those sets, A or B. Um, but there's none that don't belong to either of them. That's what a union is. And the intersection is the set of elements that are common to both sets. That means that they have to be in each set. And it turns out there's only one element that's common to both A and B, and that's 3. So B is a singleton. A singleton, I don't think I defined that yet, but a singleton is a set with a single element, with one element. So in this case, the intersection has just one element, namely the element 3. So that's what union and intersection are. It turns out union and intersection are very important in computer science and in logic. And the way you should think about union and intersection in terms of logic, you should think of union as like or. So A union B, this would be the set of all elements that are either in A or in B, or both. And intersection is like and. These are the set of elements that are both in A and in B. In this case, that's just the element 3. So anyway, that's union and intersection, pretty basic. And then the next kind of most basic operation is what we call the complement. And you can think of this sort of like a negative. What a complement is, so usually you start with something called well, I'm not going to get to this yet, but suppose you have two sets, A and B. And we write the complement of B and A, which we write as A backslash B. Sometimes people write as A minus B. I prefer the backslash notation. So A backslash B, which we would say is the complement of B and A, that's just a set of all elements in A that are not in B. So complement you should think of as like not. And uh, and then you can also have the complement of A and B. And then in general, those are different sets. So here's an example. Suppose we have A and B from the previous example. A is 1, 3, 5, 6, and B is 2, 3, 7, 8. So what's the complement of B and A? A backslash B. Well, that's easy. That's just the set 1, comma 5, comma 6. And the reason that's what it is because remember we said the intersection was just the singleton 3. Well, that's the only element of B that's not an A. I mean that is an A. So if we eliminate that one, we get all the elements of A that are not in B. And what about the B backslash A, the complement of A and B? We do the same kind of thing. We start with B, which is 2, 3, 7, 8. We just eliminate 3 because that's the element that's common to both of them. And we're left with a set 2, comma 7, comma 8. So that's complements. Again, kind of basic. I think, did I even go to the wrong slide? I think I did. Maybe I didn't. Yeah. Yeah, that's compliments. And I guess I want to say a little bit more about compliments. There usually when you're dealing with sets, you have something called the universal set or the universe. So when you're dealing with a whole bunch of sets, usually you have some big set which we call U for universe or universal set. It's just a set of all the elements we're considering. So it's kind of the set of everything. That's why they call it the universe. So you can define the universe however you want. The universe doesn't necessarily have to be very big. So for this example, I'm going to start with the universe 1, 2, 3, 4, 5, 6, 7, 8. Just the numbers from 1 to 8. And if you notice in the last example, all the elements of both A and B are numbers from 1 to 8. So they're all in this universe. And the nice thing about having a universe is you can define kind of a complement of just a specific set. You don't have to have complement respect to another set. If you like, it's a complement respect to the universe. That's what we define it. So we have a thing called complement of A, which we just write as A bar. That's A with a bar above it. And that's just defined to be U backslash A. So as long as U is understood, we can write A bar. And since our set A was a set 1, 3, 5, 6, A bar is just a set of numbers 1 through 8 or they're not in that set. And it's pretty easy to see that that's 2, 4, um, 2, 4, 7, 8. So, and then similarly, the complement of B was the set 2, 3, 7, 8. The complement of that is 1, 4, 5, 6. So again, that's pretty basic. So that's complements. And complement, like, you should think of that as not. And there's actually, I mean, I'm just going to jump the gun a little bit here. I'm going to give you a little preview. When we do logic and also when we do computation, there's the basic operations are and, or, and not. And or are like intersection and union, respectively. And complement is like not. So those are kind of three most basic operations on sets, which are pretty much the same thing as the most basic Boolean operations in symbolic logic. And so those are the operations. But now we've got kind of ordering operations. You just think of these as like less than or greater than. And the equivalent of less than and greater than for sets is subset and superset. So we say that A is a subset of B if every element of A is already contained in B. In other words, B is a bigger set. B is a set that contains all of A, if you like. So we say A is a subset of B, and that's exactly what it means. It's a set, and every element of A is already an element of B. And if it goes the other way around, we say it's a superset. So remember, for numbers, if x is less than y, then y is greater than n. So superset has the same relationship to subset as greater than does to less than. So we would say that B is a superset of A whenever A is a subset of B. And a difference between sets and numbers. Numbers are ordered. The real numbers anyway, not the complex numbers, but real numbers and every subset of the real numbers like the integers and the rational numbers. Those are ordered sets, but not every set is ordered. Um, and the operation subsets and supersets are not necessarily ordered in that way either. I mean, you can have sets that are not subsets of other sets. I mean, if you look back at the example I gave at the beginning, A equals 1, 3, 5, 6, and B equals 2, 3, 7, 8. A is not a subset of B, and B is not a subset of A. That's pretty easy to see. I mean, the intersection is a subset of both of them. That's always true. And they're both subsets of the union, but they're not subsets or supersets of each other. So subset and superset are kind of special ordering operations. And then here's just an example. I'll give some examples in this chapter just so you can see a little better what's going on. So here I give four sets. Yeah, I'm not going to read them all off, but well, I might as well. So A is 1, 2, 3, 4. B is 1, 2, 3. C is 1, 2, 3, 4, 5, and D is 1, 3, 5. I just ask which sets or subsets of which other sets, and I think just by inspection, pretty easy to see. that B is a subset of both A and C. B is a subset of A, and A is a subset of B. Sometimes people write this as a chain. B is a subset of A, is a subset of C. D is just a subset of C. It's not a subset of A or B. So those are the kind of orderings of these sets. Pretty easy to see. And again, again, you can use. I think I left something out. Yeah. Anyway, so that's all I have to say about subsets and supersets. The last thing I'm going to talk about is power sets. And this is sort of like exponentiation, it turns out. And so if you're given any set, there's a bigger set. It's always bigger, and it's called the power set of that set. And there's different notations for this. I like to write P of S. So if S is any set, doesn't matter what that set is. There's another set called the power set of S, written as P of S, and that's just the set of all subsets of S. And it turns out sometimes people write as 2 to the S, which is looks a little weird. But the reason they write it that way, it turns out if you look at the cardinal number, if S is a set with say S is a finite set, that's an easier thing to think about. If S is any finite set with n elements, in other words, its cardinal number is n, then it turns out that the cardinal number of P of S is always 2 to the n. That's why people write 2 to the S. So for instance, I give an example here where S is a set 1, 2, 3. I think you can see what the subsets of S are. I list them all here. The smallest is the empty set. And I should point out the empty set is a subset of every set, obviously, because every set contains the empty set, right? I mean, the empty set doesn't have any elements, so trivially is part of every set, if you like. The empty set's one element, and then you got the elements 1, 2, 3. Those are the singletons. The sets with just one element. There's 3 of those. And then you got the sets with 2 elements, namely 1, 2, 1, 3, and 2, 3. 3 of those as well. And finally, you got all of S. S is a subset of itself. That's another thing I should mention. Every set is a subset of itself. And there's different notations for writing subset and superset. Sometimes people talk about proper subsets. I don't do that here. But there's another notation a lot of people use for writing proper subset versus subset. Remember I showed you this horseshoe symbol for subset. I think I show it here too. When people write, a lot of mathematicians write, if they don't necessarily, if it doesn't have to necessarily be a proper subset, they write a horseshoe with a little line below it. You can think of that sort of like less than or equal to. But I don't really like that notation. I think it's kind of unnecessary. Anyway, so the power set in this case, you can see it has 8 elements. There's the set of all subsets of S. And I'm going to give you a little bit of a preview here. I might blow your mind a little bit, but this is just power sets of finite sets. It turns out that infinite sets have power sets too. And it always also turns out, and Cantor proved this, he used this thing called a diagonal argument. I will get to this by the end of the chapter. It's a little bit of a complicated proof, but it turns out that if S is any set, doesn't matter whether it's finite or infinite, its power set is always a bigger set, meaning it has a bigger cardinal number, and that's why there's different sizes of infinity. As a matter of fact, there's infinitely many sizes of infinity, because if S was any infinite set, you could keep taking power sets of that. For instance, it also turns out that the power set of the integers, or the natural numbers, it's what's called isomorphic, or there's a bijection to that set and the set of all real numbers. That's why there's more real numbers than integers. And we'll see that when we learn Cantor's diagonal argument. Anyway, that's just a little preview concerning infinite sets. But that concludes my video for today on operations on sets. Thank you for watching. Long live math, and I'll see you guys next time.